Welcome to lecture 10. Before we start today's lecture on binding, we'll briefly recapitulate what we did last time. So last time I discussed a transition system for a simple expression language in which there were no identifiers. And as I said, we are not really too bothered about various compiling or parsing issues. We would like to look upon expressions as trees, and with that in mind we gave the following transition semantics. So we assumed a transition system, a set of abstract syntax trees of integer valued expressions, of which there was an underlying set of numerals with notations for them, and we defined a transition system in which the set of configurations was the set of all possible expressions in the language. The set of terminal symbols were the numerals, and I use this general symbol to denote any of these binary operators, and we defined the transition relation by various rules. So the rules, so we had only 3 rules. Actually it's 3 rules multiplied by the number of binary operators that we have. So given 2 numerals along with a binary operator, under the understanding that this binary operator is directly implementable by the virtual machine on which this expression language is implemented, it gives you another numeral, and these 2 rules applied inductively essentially specify that we are allowing only left to right evaluations. So given a binary operator, you cannot evaluate the right operand of the binary operator till you have completely evaluated the left operand. So these 2 rules, so this rule applied several times will finally yield a left operand for a binary operator, so that it becomes a numeral, and then the right operand is evaluated. Yeah. So then I said that it's desirable in many cases to have a deterministic set of rules. In certain other cases it might be desirable to allow for a non-deterministic set of rules. So if you, for example, were to allow this extra rule, then you get a non-deterministic sequence of transitions, evaluation possibilities, and otherwise if you allow only the first 3 rules, then you have only a left to right evaluation of expressions, and depending upon taste you can pepper your semantics with whatever you require for parenthesis, or you can eliminate parenthesis altogether since you are dealing only with syntax trees. So very often for pragmatic reasons we would like to have a deterministic set of rules, and we will assume very often that we'll give only a deterministic set of rules, because that ensures that it defines the compiler for a uniprocessor quite unambiguously. Right. So today, before we start on declarations, it's necessary to give a general impression of what binding means in programming languages. The field of programming languages is cluttered up with a lot of terminology, so which many of them come from implementation issues, many of them come from theoretical issues, study of, many of them come because the terminology in different programming languages is different, so you require a unified terminology to discuss all programming languages and so on. So the notion of binding is one such, and it's often regarded as a purely pragmatic issue. So it's a good idea for us to discuss it now, starting with its with the notions of binding that are prevalent: early binding, compile time binding, runtime binding, etc. The earliest notion of binding occurs really in mathematics, without mathematicians being consciously aware of it. Okay, so you have an expression like this, let us say a double summation. I have these names. Binding very often has to do with names and declarations. So it is appropriate that before we discuss the semantics of declarations, we discuss the notions of bindings, but then we will discuss the pragmatic notions of binding too. But let us first concentrate on names. So there are these names A and B which do not matter at the moment. What matters to us at this moment are these names I, J, K, M, N. Okay. So here is this, we will assume that this is the summation in mathematics where J goes from 1 to M and I goes from 1 to N, and you have this. So this binding of I, this I is a name, and we normally use a name to denote some complex object. Okay, it's nice to, instead of having a long expression or or a long phrase to denote some complex object, especially if we are going to use it again and again, to give it a name. But once having given it a name, the issue that arises is, what does that name mean? At least in the context in which the name appears. So here the meaning of the name is that I goes from 1 to N. I can range from 1 to N, and that is a binding occurrence. So this is the introduction of a name and the introduction of the name along with its meaning. So this entire sigma I equals 1 to N has I as a binding occurrence here. Similarly with J in this sigma. Okay, now having introduced the name and what it denotes, I am now free to use that name for some purpose. So here this I here denotes an applied occurrence. So having defined a binding occurrence for the name, one has an applied occurrence. So similarly with J. However, the K here, for example, has a purely applied occurrence without any binding occurrence. Okay, presumably this whole expression was lifted out of context and placed here. So hopefully, if it is a well defined mathematical context, then K would have a binding occurrence somewhere else in the context. So binding occurrences could occur somewhere fairly deep inside some mathematical object. Similarly, N and M would presumably have some binding occurrences somewhere, and they are called free occurrences. So the whole issue has to do with names and naming, and what do names mean, and when does a name have a meaning. So here is a case where the binding occurrences precede the applied occurrences. Similarly, if you were to take this double integral, here the binding occurrences are dx and dy, of course with the appropriate integral symbols. Okay, the binding occurrences are dx and dy, and the applied occurrences actually occur before the binding occurrence. So the binding occurrence appears after the applied occurrence. In each case, for each of these bindings there is a scope. So the scope of this J starts from here, from its first binding occurrence to the end of the phrase which can have a binding occurrence, which can have an applied occurrence. The scope of I similarly starts from here and goes to the end of a possible applied occurrence. So similarly in the case of this double integral, the scope of y is in the dark blue region, wherever it starts essentially from the from this integral symbol and goes right up to where the binding occurrence is, and the scope of x starts from this integral and goes right up to the binding occurrence. So this is an example of when the binding occurrence occurs after the applied occurrence. If you look upon this as a string or as a tree, even as a tree, then it's the binding occurrence occurs as a node of some right subtree, whereas here the binding occurrence precedes the applied occurrence because it occurs as a node of a left subtree.
What is the definition of a binding occurrence?
This is the definition of a binding occurrence is just that it's the first introduction which somehow gives it a meaning, okay, but meaning is not part of the syntax, okay. So for example, what is the meaning of this sigma? What is the definition of this sigma? It might differ. I mean, I have just assumed that it refers to summation, but that's not necessarily always valid. A binding occurrence usually means a declaration. In programming, it means a declaration. So there are, and binding occurrences and applied occurrences occur everywhere, in fact. So in every, for example, in logic you have these quantifiers, right. So you could have a quantifier like for all x there exists y and some statement in terms of, let's say, some predicate p which has maybe several free variables, right. So you could have maybe a z, you could have x, you could have y, right. This is a common thing, and it doesn't necessarily, so here you have this binding occurrence of x, here is the binding occurrence of x, here is the applied occurrence of x, whatever this predicate is, some statement. So the predicate is just some statement. Here you have a binding occurrence of y, and you have an applied occurrence, one or more applied occurrences of y in this predicate p, and the scope of y is delimited by this quantifier, the scope of x is delimited by this quantifier, right. And z is free. If you look at any of your school problems in mathematics, one of the first statements you would say is let x be the something something, and then the rest of your context is maybe a solution towards x or a solution involving x. That let x be something is a binding occurrence, and all other occurrences which use that x are applied occurrences. In every problem you might have a let x be something and let y be a something. In each case, the moment you state that, you've got a binding occurrence, okay. In different problems the different x's have different binding occurrences, and they have therefore different applied occurrences. So within a problem, when you say let x denote something, then that x has the scope restricted to your solution to that problem, right. So this is very much part of also natural language, it's, so to define it is very hard, but to understand it is reasonably easy. the fact that you first introduce a name and you explain it through some meaning. You give it a meaning, and that is a binding occurrence. Later, assuming that meaning, you can always use that, and every use of that name is an applied occurrence. Yeah. So in programming, you have, let's look at a typical Pascal kind of environment. So I have this constant declaration. So in most cases in programming, binding occurrences occur as parts of declarations. That's when you introduce new variables. As in the case of mathematics, the binding occurrence in several languages could actually occur after the use of that name. So for example, in mathematics, it's also quite common to say, let some expression be something where you have already introduced new names, which are all applied occurrences, and then you write where those new names mean these things. So those are the binding occurrences. For compiling reasons, many programming languages like Pascal, actually for efficiency of compilation, not necessarily because that's the only way to do it, but for efficiency reasons, many languages actually insist that binding occurrences should precede use or should precede applied occurrences. So you can take something like this. So here's a constant declaration in a language like Pascal, though I've used commas, so it's, you could equally well take it as a language PL0. Yeah. So m equals 10, m is a constant, 10 is a literal, pi equals 3.14159, a equals pi star m star m. In each of these cases, this is the first introduction is a binding occurrence, and all later uses of those names are applied occurrences. Yeah. So in the case of a variable declaration, you have a binding occurrence when the variable is first introduced, and everywhere that variable is used, you have applied occurrences, including on the left side of the assignment. All these are applied occurrences. Yeah. Okay. Right. So in a language like ML, the typical binding occurrences look like this. A let statement is a typical occurrence of a binding of an introduction of a binding occurrence. So let some name x equal some expression e naught in some other expression e end. Okay, where I'll assume that this expression e actually uses this x. So this is a binding occurrence of x, and any occurrences of this x inside e would all be applied occurrences. Yeah. So in a typical ML session, you also have things like you introduce names in the beginning as val y equals something, val as pi equals 3.149, right. So all these are binding occurrences, and what you are doing is you are creating an environment of names along with meanings, and you are using those names in your subsequent expressions, right. So now in addition to, the most important reason for having binding occurrences is usually the introduction of names. But in the case of so what are all the possibilities? So a binding occurrence usually either defines by introduction or redefines an existing name. Yeah. So names are identifiers. Identifier is the more common term, and an applied occurrence just refers or denotes the meaning defined by the appropriate binding occurrence, right? So in general, what you could the semantics of the language should actually specify what is a binding occurrence and what is an applied occurrence, right? So you could think of a declaration like this in Pascal as defining some binding occurrences and also using them, applying them somewhere. And in the process, so essentially what we are saying is that we require names because we cannot always be using these arrows. Okay, so you could in theory, if you just had these arrows, we'll see that maybe when we do the lambda calculus, but it's in theory it's possible to completely get rid of names if you had some complex way of referring to some object or some meaning. Yeah. So in a language like Pascal, which insists that all declarations precede use, the arrows will all be upwards. Further, in a complete program of Pascal, all variables will eventually be bound, all identifiers will be bound. There will be no free identifiers. And by a complete program of a language, I also include the libraries which you might be using. So for example, in a typical Pascal program or a Fortran program, if you use the function sin x, then that sin has an applied occurrence in your program. However, you might never actually define it within the program, because it's already available as a library. So a typical environment of a Fortran program includes not just your program, but also all the binding occurrences that are defined in the global environment through libraries or through whatever is the initial global environment provided by the system. Yeah. So let's look at the various kinds of bindings. So if you were to look at the meanings of bindings more closely, what we will see is that in the case of an imperative language, right? So let's just consider two simple instances. So we'll take a Pascal like and an ML like language. A Pascal like language has these constant declarations, all right, and has variable declarations of this form, let's say. An ML like language, a functional language, has declarations of this form, okay, and within let expressions and so on and so forth, which are unnamed functions. So you also have function names, for example. Okay, here you have things like this, which is some expression, right. So in this case, in the case of an imperative language, this constant declaration M gives you, this is a binding occurrence of M, which binds the name M to the value 10. It's a name value binding, okay. And in fact, the functional language declaration of this form is exactly the same. It gives you a name value binding. Yeah. So that's what binding means. So the meaning of M is just the value 10 in this scope, within the scope in which it is declared, right. In imperative languages, further, there are these variable declarations which actually denote locations, okay. So the variables in an imperative language are actually have name location bindings. There are further, so when you have a begin end with this variable being updated, okay. So in this place what happens is that, so the variable location binding remains unchanged. However, there is also a location value binding in the case of a variable which can be changed by commands. In a functional language in general there are no locations. I mean, the whole idea of a functional language is that it's abstract enough not to include the notion of a memory as part of the language, and therefore updates and assignments are prohibited. So a variable in a functional language is really something like a constant in an imperative language. A variable in a functional language is just a name value binding. And in languages, in most cases, the function f is also you can also look upon the function of a function itself as a value, and a function declaration itself is another name value binding. Whereas variables in imperative languages implicitly assume the existence of a notion of memory or store, and they have an indirect level of, they actually consist of two bindings: a name location binding, which is, location is just pragmatically speaking it's just a memory address, okay. So there is a name location binding, and then there is a location value binding which might be changed depending on what are the contents of the location, how you are updating that location, right. In a functional language this complication of locations or memories is completely abstracted away, and you have just name value bindings throughout, and that is the essential difference between a functional language and an imperative language, right. So you could have, so what people consider a variable in mathematics is really a variable constant, variable in the sense that it is unknown, but that its binding is the same. Over the scope in which there is you have a variable, it represents the same value in a mathematical problem. Similarly, in a functional language, in a functional program, over the scope in which a variable is declared, it represents only one value, unlike an imperative program where the variable actually gets updated in this form. So what remains constant in an imperative program is only the name location binding. The location value binding changes, it keeps changing constantly, right. So the notion of a variable in a functional language is really the notion of a variable in mathematics, which is really something that does not vary. over time. It is a variable in the sense that it is in mathematics, usually it's used as, the name variable is used for something that's unknown, but something that has a constant value. And in a functional language, it is just, since it's just a name value binding, it is always constant over the scope in which the binding is effective, as opposed to a variable in an imperative language, which actually what is constant is only its the binding between the name and the location or the address in which that variable is stored. So the name x just denotes a particular address in memory, pragmatically speaking, and that's the only thing that remains constant over the scope in which this binding is effective. And it does not say anything about the location value bindings, which means, which loosely speaking in the case of memory locations, it means the contents of that memory location, which can keep changing. Yeah, so you can have various kinds of, but we are more interested at this point, since the issue of bindings came up, it was necessary to point this out, but we are really more interested in bindings from the point of view of declarations, because we eventually have to give the semantics of declarations of, let's say, some language like PL0, right. So let's look at the various kinds of bindings that are possible. So you could have nested bindings, right. So for example, here is a typical Pascal like program fragment in which you have a declaration of the identifier I here, and you have another declaration of I as a variable here. All applied occurrences of I within this begin end block refer or mean whatever name location binding has been specified here. Okay, all occurrences of I here denote whatever name value binding has been specified here, right. So and of course we have these normal lexical scope rules, right. So the scope of the variable I declared here extends through this procedure. The scope of this constant I extends through the entire through this entire fragment, provided there is no other declaration of I in an inner scope, and any other declaration of I is a hole in the scope of the constant I. Yeah. So a scope just gives you an extent in the program text in the case of what are known as statically scoped languages, gives you an extent of program text over which a binding occurrence applies, right. Okay, so you can have of course this also, as a language designer, the one question is are nested bindings necessary? I mean, why does a language like Pascal, which for example boasts of simplicity, it's a good language for learning programming and so on and so forth, and why do almost all block structured languages allow nested bindings, which can only be confusing? For example, they affect readability, because every time there is a reference in the main code to an identifier, you have to find the declaration where the actual binding appears. Okay, and if you allowed nested scoping like this, if you allowed the creation of holes in the scope of a given identifier, then all you are doing is you are spoiling the readability of a program. Secondly, it also makes it necessary for a compiler, every time an occurrence occurs, every time there is an applied occurrence, it makes it necessary for a compiler or a parser to look for the appropriate binding occurrence and verify various things, like, I mean, are you using, for example, within this scope, are you using I only as a real variable or perhaps it should be checked that it's not being used as a character or a string, yeah, or as a pointer. So it puts an extra overhead on the compiler and the runtime system, especially in a language like Pascal, which does type checking, as to where exactly is the binding occurrence and whether the meaning specified by the binding occurrence is being explicitly followed here. So a simple solution could just be that just ban all nested bindings, so that everything is, so that every time you declare a new scope you have only new names and there should be no problem at all. But it's so but the problem is that very often when you have a program developed by a team, what you would like to give a programmer of an individual procedure, which might go deep into some program, is the flexibility to use his or her own names for the variables that he is using. And so which means that that particular programmer, if you disallow nested bindings, then that programmer would have to know all the global names before deciding what should be the new names to be used locally within that procedure, which can be quite a task. Which means that the first thing the entire programming team should decide are what are the names for various global variables. And in a really large software project, that can be a constraint rather than a facility, you know. But however, as I said, it spoils a lot of things. However, it spoils readability. It's quite disastrous in languages with default bindings. I'll just show you what default bindings are. And then of course it complicates debugging. For example, suppose you intended to intended to introduce the name I in your scope, but you actually forgot to declare it. But there is an I in some other scope. Then the debugging process becomes quite complicated, because every time that I is considered to be global. So for example, so in this case, if you were the writer of the procedure P and you forgot to introduce this declaration, then it will be taken that this I always refers to some global occurrence, and you will be wondering why your program doesn't seem to work as you expect. So it really complicates, and this I may not be just in one outer scope, it might be a global, and your procedure might be deeply nested inside somewhere. So nested bindings complicate matters quite a bit, both in terms of debugging and readability. But what really clinches the issue, for example in the case of Ada, is that everybody uses I, J and K as a counting variable in a for loop. I am not joking. This is something that was actually stated in a discussion on the Ada language, that everybody in the world uses I, J and K as a counting variable, and so you should give the programmer the flexibility to decide, especially when the counting variable has no other significance except as a counter for a for loop, for example. We all use just I, J and K. That's if it has no particular significance, right? So so nested bindings are here to stay, even though they complicate some matters. So in languages like Fortran, for example, they had this very funny rule. They said that you don't need to have a declaration. So which means that you need not have binding occurrences. You need to have only applied occurrences. However, the applied occurrences will have default bindings in this fashion. So any name that starts with I, J, K and L, which does not have a binding occurrence, is taken to be an integer variable. Further, any identifier that starts with any other letter and which does not have a binding occurrence is taken to be a real variable. right. So they had these things which actually makes matters really bad, because what can happen without these binding occurrences is that you might actually have a variable starting with I, which you choose your identifiers so that they reflect the problem context, right. You might actually have something starting with I, you intended it to be a real variable, but you forgot to declare it. The Fortran compiler also compiled it, the runtime system is executing it, but you are getting disastrous results, and you may never know about it, especially if you are solving a problem for which there are no known test results, right. There is a legend that some of these one of the disasters, space disasters of one of the satellites, was due to the fact that it was written in Fortran, where there was this supposedly do statement in which a comma was mistakenly replaced by a period, and therefore that entire do statement was taken as a real variable. So do 10I equals 1 comma 15 means you execute that loop 15 times, but if the comma is replaced by a dot, then this do 10I is taken as a real variable, since it starts with D and there is no binding occurrence, with an initial value of 1.15. Okay, so these are, there is a legend that one of the Venus disasters was due to a Fortran program bug of this kind, which definitely is never detected by a compiler. It is definitely not detected by a runtime system, because there are no binding occurrences, because of the default bindings. So what it means is that small typographical errors, spelling errors, which we are making all the time in our programs, would get bound by default to something other than what we intended them to be. Yeah. So that's one of the reasons why later languages like Algol 60 and so on insisted that there should be binding occurrences for every new identifier. There are of course some certain special kinds of implicit, there are certain bindings which are implicit. For example, you might in some, this constant declaration is not really intended to be in this scope, it could be in some outer scope. You could have two records R and S in a Pascal like language defined this way. So this C is a component of this record declaration which has some type. So this is a binding occurrence of this C within the record, but however the binding is that C is only bound to all variables that have this record, that are of this type. So the C is not explicitly bound either to this R or this S, both of which are of this record type. So the binding occurrence can actually be decentralized, can actually be stretched out. Part of the binding occurrence can be here, the other part of the binding occurrence can be in a with statement. Right? So within this with statement, this C actually gets perfectly bound to R. In this with statement, what all references to C actually get bound to the S, and the normal scope rules apply. So within this, so this with begin end is a scope, this with S do begin end is another scope, and this with R do begin end is a hole in the scope of the C which is bound to S. Right? So pragmatically speaking, even binding occurrences can actually be stretched out. I mean, not all, the full meaning need not appear at a single binding occurrence. It might be distributed across two or more constructs, which is actually not very surprising in the case of variables, for example. There the binding occurrence, the name value location, the name value binding occurs at one go, and the value and the location value binding occurs several times in different places. Okay. Even the name location binding in the case of variables does not fully occur at that point in many cases. If you look at the implementation of a language like Pascal, what happens is that a name relative location binding occurs at compile time, and relative location to absolute location binding occurs at runtime, because of the structure of a block structured language is such that you never know at compile time when you are using a dynamic memory allocation. You never really know when you are going to call that procedure, and therefore what is going to be the base address relative to which that variable has to be located. So even that name location binding, from a, when you look at it purely pragmatically, can be stretched out across the entire spectrum from compile time to runtime, right. So there are other kinds of bindings. For example, in all these kinds of in all kinds of bindings that we have discussed so far, you have an identifier denoting a single object, whatever that object might be. But you have also what is known as overloading, and the most common overloading available in all programming languages is the overloading of addition and multiplication and subtraction. Here you have addition, these operators are also identifiers. They have their binding occurrences are in the global environment in most high level programming languages. However, even in the global environment, they have two different meanings depending upon the operands, right. So there are actually two different identifiers: integer addition and real addition or floating point addition, integer multiplication and floating point multiplication. So what exactly is the binding? So within the same scope, these identifiers have two different bindings simultaneously available. So there is no creation, there is no overriding of one binding by another. The overriding is completely local and it depends entirely on the types of the operands, right. So this is known as an overloading, and this overloading has been, in the case of Pascal there is of course another obvious overloading, which is that you have a function name and you have a variable name with the same you have a variable with the same name which stores the result of executing the function. So that is a case where you have a function name which denotes, well, a function object, but the same name within the same scope also denotes a name value binding in which the value of the function is returned. So besides this overloading has been carried across to more modern languages also much further. For example, in languages like Ada, you can have the same name bindings representing different objects which are distinguished just by some simple thing like the types of parameters. So in the case of procedures, you can use for example, within the same scope you can define two or more infix plus operations. For example, you might do plus for matrices of some kind, you might do some plus to denote concatenation of strings or whatever, but just based on, so in addition to the global bindings of plus which denote integer addition or real addition, you have two more new bindings and all four of them occur simultaneously in the same scope, and the only distinction is either based on the types of operands or on the types of parameters, which is mathematically the same thing, though in terms of language implementation it is different. It depends on the types of operands or order of operands. Just on those syntactic basis you have you have a distinguishing capability between different bindings for the same name available within the same scope. Okay. Lastly, we have so let's look at these various kinds of bindings from an implementation viewpoint. So you can have these constant variable bindings. Some of them are compile time, some of them are runtime. Mostly in languages which are which believe in a static type checking, or at least which allow the facility of static type checking. You try to do the bindings as early as possible at compile time. In many other languages you actually do it at runtime. Languages, even these identifier value and identifier location bindings are often done at runtime. This is typically with dynamic data structures. Even in Pascal you have various name location bindings occurring at runtime, right? The language Lisp, for example, carries it much further. So languages like Snowball and Lisp believe in runtime bindings as opposed to compile time bindings. Yeah. So they believe in what are known as late bindings. So as a result, so you can take the entire spectrum of doing bindings, and you can actually, well, loosely speaking, order languages in this fashion. So if you look at Fortran and COBOL, Fortran and COBOL do very early bindings. In fact, the difference, so everything is done at compile time. The complete memory allocation is done at compile time. So even if the Fortran program has relocatable code, the bindings are completed. For example, the bindings for variables, that is name, memory address, absolute address bindings are done at loading time before runtime begins. Okay. A compiled Fortran program might still give you relocatable code. That means it might only give you relative addresses, but at loading time, during linking and loading, the entire address calculation is completed for every variable. For every name, the address calculation is completed before. So as a result, and Fortran also has a static memory allocation. So it's only, since you do very early binding, you have to decide on exactly the kind of memory allocation well before you start running the program. So a static memory allocation is done very much like in the case of assembly language. Every code segment is followed by a data segment for that code. And so you have very early bindings well before runtime. There are no allocations done at runtime. You have a completely statically partitioned memory, and all absolute addresses are calculated well before any program, before the execution of the program. At most they are delayed till loading time. So so Fortran has this property, and as a result Fortran programs are very, very fast. Because the overhead of memory allocation and changing bindings and so on is not there. But they are also quite inflexible in various ways. I mean, you can't have dynamic arrays and so on and so forth. You can't have dynamically created data structures. So at the cost of flexibility, you have very fast executions. If you look at Snowball and Lisp, since the bindings are all late and most of them are done at runtime, what it means is that you have to do fresh memory allocation, you have to do fresh you have to do all the bindings like name address bindings at runtime, which means that you also require a garbage collector which tells you exactly what part of the memory is being used, what part of the memory is not being used, so what is available, the request for more memory, all that is done at runtime. So as a result, these languages are in general very slow, but they are very highly flexible. You can do the data structuring completely dynamically with absolutely no static allocation. right. So most of the allocation is on the heap in such languages. Languages like Pascal, Modula, Ada and ML actually follow a somewhat in between policy. I mean, they do a name relative address binding at compile time, but they postpone the relative address absolute address binding to runtime. In the case of ML, in the case of C, actually most of the allocation is done as in the case of Fortran, mostly static allocation, except where the C compiler detects recursion. It detects recursion by a graph construction process, and the moment it detects recursion, it realizes that you really cannot do the static allocation that you do in Fortran, because you do not know how many recursive activations of that function are required. For each activation you require to do fresh allocation. So whatever is not recursive, it follows the policy of Fortran, and only for recursive invocations it takes a late binding view, and actually there is a graph construction process by which it detects cycles in the graph and therefore detects recursion. Yeah. So C programs are very fast because they do most of the bindings at compile time. Yeah. So in the case of Pascal, Modula, Ada and ML, there is of course extra overhead in the form of type checking, which has its own overhead. At least in the case of Pascal, it's just type checking. In the case of ML, it's type inferencing, so which means there's a huge computation process involved in just compiling a function, just to determine all the types. Since you don't require to specify types in the function, there is a type inferencing system which actually solves a system of equations on types, and so there is an extra overhead at compilation. Yeah, so the next time we'll start off with actual declarations in PL0 and then go on to